Alright guys, so today we're going to start talking about torque, and torque is a twisting force or a rotating force. Torque is what causes something to rotate. If we're being technical, torque is what causes something to have an angular acceleration. So, for our example today, we're going to look at trying to loosen a bolt. So, let's take a look at a wrench and a bolt. So here is my bolt. And here is my wrench on my bolt. So, of course, we want the bolt to rotate. If we were trying to loosen the bolt, we would want it to rotate in a leftward or a counterclockwise direction. If we were trying to tighten it, we'd want it to go in a clockwise direction. And so, of course, to turn the bolt, what we end up doing is pushing or pulling on the handle of the wrench. And there's lots of ways I could push or pull on the handle of the wrench. So, for example, if I'm trying to loosen it, I could grab the wrench here and pull up. Okay? Or another option, so that's F there, or another option would be to grab the wrench out near the end, and I could try to pull out. Now, of course, hopefully you guys realize that the first option there in pink would cause the bolt to loosen, and the option there in white would not, because of the direction of the force that I'm applying. Now, a third and even better option would be to grab the wrench out near the end but then push up. And so the idea here is that both the pink force and the blue force there would both produce a counterclockwise torque, and the white force pulling to the right would not produce any torque at all. But the blue force out near the end would produce more torque than the pink force near the middle, assuming the blue force and the pink force were the same value. So, torque not only depends on how much force you apply to your object, but it also depends on where that force is applied, and it depends on the angle at which you apply the force. So when we talk about where the force is applied, we can see that the pink force is applied some distance, we'll call D1, from the axis of rotation, which is the bolt, and we see that both the blue force and the white force are applied at a greater distance, D2, from the axis of rotation, or the which is the center of the bolt. And then the third thing we notice is that F in pink there is applied at a 90-degree angle to the wrench handle. Also, the force in blue there is applied at a 90-degree angle to the wrench handle. But of course, the force in white is applied, depending on how you look at it, either a 0 or a 180-degree angle to the wrench handle, which is why the torque produced is different. So when we want to calculate torque, the basic idea then is that torque is going to always equal F d sine of theta. Okay? And because force is measured in newtons and distance is measured in force is measured in newtons, distance is measured in meters, torque is measured in Newton meters. So we can quickly see, looking at the equation, the bigger the force, the bigger the torque, but then also the bigger the distance from the axis of rotation, the bigger the torque. And then finally we see that torque also depends on the angle, and the closer that angle is to 90 degrees, the more the torque will be. So when theta equals 90 degrees, that's when we're going to get our maximum amount of torque, because the sine of 90 degrees equals 1. But if that angle equals 0 degrees, then we are going to get 0 torque. And that's because the sine of 0 equals 0. Also, if that angle was 180, the sine of 180 equals 0. So when we measure that angle, it's important to understand that we're measuring it from the lever arm. So if this is my lever arm, the wrench handle there, then I see that the pink force would have a theta of 90 degrees, the blue force would have a theta of 90 degrees, and then the white force you could call 0 or 180 depending on how you looked at it. So of those three forces there, the blue force, F, is going to produce the greatest amount of torque because it is farthest from the axis of rotation and it's at an angle of 90 degrees. Alright, so a very common problem to see on the AP exam, especially on the multiple choice portion, is some sort of torque balance. And we can have torque balances where we have a massless stick, or one where we have a stick and we have to account for its mass. So right now we're going to look at one with a massless stick. And a torque balance is basically like a seesaw. So if I took some mass, M1, and stuck it on the left side of my seesaw, of course the whole thing would turn counterclockwise around the fulcrum there in the middle. But if I took another mass, M2, and stuck it on the torque balance as well, if I use the right amount of mass, then the whole thing will maintain equilibrium. So of course I have three forces going on here. I have M1G going down on the left hand side, and I have M2G going down on the right hand side, and I would have a normal force going up from the fulcrum. And so of course, to be in equilibrium, the first thing that has to be true is the upward force has to equal the downward force. But there's more to it than that, because we also don't want this thing to twist and turn. We want it to stay level on the fulcrum. That's the whole idea of a torque balance. And so for that to be true, not only does the net force in the y direction have to equal 0 and the net force in the x direction have to equal 0, but the net torque has to equal 0 as well. And for the net torque on a system to equal 0, then the torque in the counterclockwise direction has to equal the torque in the clockwise direction. So I have two torques going on in this problem. The normal does not create a torque because it's applied right at the axis of rotation, which means its D would be 0, so it doesn't produce a torque. But M1 and M2 both produce a torque because M1 is some distance D1 from the axis of rotation, and M2 is some distance D2 from the axis of rotation. So my counterclockwise torque is produced by M1 because M1 wants to make the left side go down, making the whole thing turn in a counterclockwise direction. So my torque from M1 is going to be M1G, because that's the force produced by mass 1, its weight, times D1. And then in this case, theta would be 90 degrees because my lever arm, my massless stick, is horizontal and weight is a vertical force. So the angle is 90 degrees and the sine of 90 equals 1. So we don't have to worry about the sine of theta. And then my clockwise torque is produced by mass 2. And so the clockwise torque is going to be M2G D2. And so then what we'll see is the G's cancel. And so for this to be in rotational equilibrium, for it to be balanced, M1 times D1 equals M2 times D2. So M1 and M2 do not have to be the same mass as long as the heavier mass is closer to the fulcrum and the lighter mass is further away. So that's the whole idea behind a torque balance.